Thanks very much, Lisa. My name is Mark Kocherovsky. I'm a graduate student at Michigan State University with Dr. Wolfgang Bonzaf. Um, it's it's an honor to be here at my first A-Life. I wish I could join in person, but this morning I tested positive for COVID. So if you'll just bear with me, I'll tell you about crossover in Cartesian versus linear genetic programming. So we'll keep the very basic part short for time. Genetic programming, instead of optimizing a discrete parameter, you're trying to develop a program. In our case, we're doing symbolic regression. We're training functions based on a given data set. And traditionally, we use tree genetic programming. And as we traverse the tree, we get an expression. Mutation can either be performed on points or on subtrees, and then crossover is also performed on subtrees. And then your fitness will be your error compared to like the ground truth data set. So this is a very small tree. As you traverse the tree, you get intuitively like this mathematical function. But the thing is, TreeGP is a bit clunky, and it's also vulnerable to bloat. It can become unreasonably large without any gain in fitness. So new paradigms have been developed to resolve this issue and improve convergence. In linear genetic programming, we set aside a vector of memory to read to and write from using a linear sequence of instructions instead of this tree model. So in our example, we have register 2 is equal to the input register plus 7. Register 2 is equal to itself times 3. And then we have register 3 is equal to register 1 times register 2. And you'll notice that in the output, in the final line, register 0 is equal to register 2 minus 6. Of course, register 3 does not contribute to register 0 at all, but it's still an instruction. And that's called an intron. And we keep it because it might provide useful genetic material for future generations. In Cartesian genetic programming, we represent our program as a directed acyclical graph with a fixed length representation. So each node is either an instruction or a terminal, and its input is the output of two nodes before it. And what we are changing in this case when we involve is the connection genes. We'll see that in detail in a bit. So crossover has been repeatedly observed to hinder Cartesian genetic programming search. It tends to converge towards worse fitness values, and it takes much longer to do so. So in practice, we use 1 plus lambdas, 1 plus 4 normally. However, linear genetic programming, you have to use crossover to do search. But both of these structures, the linear and the Cartesian structures, are very similar because you can very easily draw one as the other. And typically, we cite Clegg et al.'s work from 2007. And I'm not sure how visible this is on the screen, but it demonstrates that with crossover, the fitness trends towards 0 much slower than with only mutation. So in the literature, there's quite a few examples of crossover operators which are claimed to overcome this barrier. I won't go through all of these in depth, but we will see one in action soon. But there are very few studies of the phenomenon itself. So what we're looking at is people are trying to make better operators, but without an understanding of the problem with the traditional crossover operator. So in this work, we depict an LGP individual as a two-dimensional matrix. Each row is an instruction, and each instruction has a destination register in the set of memory, and a binary operator, and hence 2 operands each. And each operand is another set location in memory. And that gives us something like this. This is a very small, simple program, and it's drawn as a directed acyclical graph for convenience. Note that the percent sign here does not indicate the modulo function, but the analytic quotient, which is a protected form of division to ensure that you will never have uh, a value divided by 0. We also have a linear scaling to our output, and this has to do with our fitness function, which we will also cover shortly. In Cartesian genetic programming, an individual is typically, traditionally, a one-dimensional vector. Each node is however many components, but we only do this for the crossover function. Typically, for everything else, we keep the CGP individual also a two-dimensional matrix. Each row is a node. Each node has a binary operator and then 2 source nodes. And then that's connected with pointers to output nodes. And that's just easier to operate on, from a programming perspective. I don't want to have to tell the program to look at every third value in the vector and then every third plus 1. This just makes more sense. And we can get something like this. And this is a different problem, but you can see that each node takes the result of two other nodes, which themselves can be an operator or a terminal. So first we need to demonstrate that this phenomenon exists, because if we tried one-point crossover and it worked first try, the field in general has some explaining to do. So we tried 8 methods, the canonical 1 plus 4, 16 plus 64 CGP, which essentially means that you have 16 parents, each one has 4 children, but it's still no mutation is done. And then a set of 40 plus 40 sets, which would be CGP 1 point, CGP 2 point, CGP with the subgraph method, which is what comes from one of the papers I showed earlier. And the subgraph method, you are trying to only swap over non-intronic nodes. That is to say, the only nodes that actually move between individuals are those that will be activated, and the individual is also rewired to ensure continuity between the two halves. And then uniform linear genetic programming. So we take half of each parent and combine them together, and the rejected halves become the second child. 1 point linear GP and 2 point linear GP. We have 10,000 generations in each run, a tournament size of 4, and an individual can be at most 64 instructions. Although, of course, in CGP's case, this is fixed to 64. We tested on 7 problems from the literature. We used the same problem set as Calculate's 2020 paper, where he introduced subgraph crossover. So we did 50 runs per problem per algorithm. There's around 2,800 trials. And we had tournament selection with elitism using 4 contestants. Now, these are relatively simple problems, but it's also a good opportunity for us to test the correlation fitness function described by Hout et al., which uses the Pearson correlation not to simply check the local error between the predictions and the ground truth, but it will primarily concern itself with the shape of the graph. This is why linear scaling is necessary, because you might find that the program has learned to perfectly replicate the shape, but it might be several orders or several factors away from the actual points. And we just use a simple NumPy polyfit function for that. So this is a very large graph, but what we see here is for each problem, the box plot of each method. And what's important to note here is that CGP with crossover is routinely outperformed by their LGP counterparts. And CGP with mutation only significantly outperforms the CGP with crossover. So I think it's fair to say that we have reproduced this problem. So what is exactly the difference between LGP and CGP? It's still going to be a set of instructions executed one by one. So we use a simple alignment scoring algorithm that just tells us how many instructions would we need to move to change like one individual into another individual. We measure taking a couple, the best parent and those parents' best child, and then it assigns it a score. So here we see the average similarity between parents and children for each problem and with each algorithm. And we see that LGP clearly produces children that are more similar to their parents than CGP. Now, why might that be? LGP makes use of intermediate calculation registers that they're stored in memory, and you interact with these, whereas in CGP, you simply call the instruction beforehand and just take that output without question. Now, LGP individuals can also be of different sizes, whereas CGP is canonically fixed to a certain size. So we took COSA 3, which is typically the hardest of this set of problems. And we tested
Mark, you have 2 minutes. Sorry.
Oh, yeah, that's fine. We tested LGP with different combinations of registers and whether or not it was fixed length. So what we see is that you need to have sufficient registers, and you need to be able to change the length of the program to perform effective search. So registers are important because we hypothesize, because without registers, you see severe destruction. We hypothesize that the registers serve as anchor points for high-fitness substructures. If one instruction is changed and one substructure is then irreversibly damaged, because it is indirectly communicating with the other instructions through the registers, the other instructions are not necessarily affected, and the other substructures are not necessarily heavily damaged. Whereas with CGP, if you change a single connection gene, you have an entirely different graph, especially towards the output. Size regulation could also be important because we think that this allows crossover to be more flexible. You're less, because you can have more choice of the crossover point because you're deciding for two of them, one for each individual. You're less likely to amputate existing high-fitness substructures. Whereas in CGP, you just choose for one, you make a cut, and what you get is what you get. So we've reproduced the CGP crossover problem. We've shown that LGP is less destructive than CGP when it comes to crossover, and we think it's because of the presence of intermediate registers and program length variation. So in future directions, we're studying more kinds of metrics. We think it's possible to develop new designs and operators using this knowledge, and of course, to more in-depth study our hypotheses to come to a decision one way or the other. And I thank you very much for your time, and I'm happy to take your questions.